All right, great to see everyone. It is good to be back here in Pune after, I think it's been probably almost 15 years since I was last here. The town has grown an awful lot in the last 15 years, or since 2004, 21 years ago. So this is a talk meant for people who may not know a lot about the accelerating universe, but it is meant to be the story of how we got here from beginning to end, because the story of the accelerating universe is really a story of the universe from beginning to end. So let's start at the very beginning, hopefully. Make sure our equipment is all working here. Interesting. One second. All right, I can see I'm going to be doing it from we really did test this just beforehand. All right, well, we'll start. Let's start with the beginning, the Big Bang, the rise of the universe, part 0. Long ago, before stars and galaxies existed, something happened. The universe, as we know, was created. We call this time the Big Bang. Now, we don't really know what the Big Bang was. We don't know what happened before the Big Bang. Just to get rid of that question, if you ask me what happened before the Big Bang, I'm going to tell you my honest answer, I don't know. But we know something happened, and we know right after the Big Bang that things were hot, they were dense, things were expanding in all directions. We know that hydrogen and helium created, and 380,000 years later, we could see the afterglow of the Big Bang in something that we call the cosmic microwave background. And the cosmic microwave background is an image here shown by the Planck Observatory up in space that looks at microwaves. And this is a projection of the entire sky looking out, obviously, onto a single screen. And each one of those little bumps and wiggles we're going to talk more about in a bit are literally tens of thousands of galaxies today. That afterglow of the Big Bang, the universe is glowing at about 3,000 degrees in temperature. So not quite as hot as the sun, but still very hot. Now, if we go through and look at the beginnings of cosmology, I would say it really started in the early 1910s, 1920s. The person who had access to the largest telescope in the world, Edwin Hubble, was looking at what we called at the time nebulae. And he was trying to figure out how far away they were, and he did that by using the very simple piece of physics that the further away something is, the fainter it appears. And so by looking at, for example, the brightest star in a galaxy, he could judge the relative distance to another galaxy by simply how bright the brightest star was. So if the brightest star was a bit fainter, then you knew it was a bit further away, and you could use 1 over the square root to figure it out. Someone who most people don't know, Vesto Melvin Slipher, had actually gone through and looked at many galaxies, and using the Doppler shift, which causes light to get stretched by the motion of a galaxy, for example, he deduced how fast galaxies were moving. And to everyone's surprise, almost every galaxy was moving away from us. There was a handful, like the Andromeda Galaxy, coming towards us, but almost every galaxy was moving away from us. And Hubble in 1929 put these things together in this diagram. Now this diagram is what science looks like. He plotted the redshift, how much the light was stretched by what they thought was the Doppler shift, but what it turns out more to be the expansion of space itself. versus how far the galaxies appeared by how bright their stars were. So the galaxies that had bright stars here, ones that had faint stars, you could figure out their distance here. And you could see the further away, the faster the motion. And from this, he could proclaim that the universe was expanding. Now, I have a cartoon. Watch it carefully. I've just expanded the universe in the cartoon for you. And if you look at this cartoon and we compare before I expanded it and after I expanded it, you see that nearby objects have moved a little bit, distant objects have moved a lot, and so therefore this cartoon kind of illustrates that in an expanding universe you see what Hubble saw. The further something is away, the faster it is moving away from us. Now there's an interesting thought experiment you can do. If the universe is expanding, what happens in the past? So if we run the universe in reverse, we get to a point where galaxies get closer and closer and closer, and everything is on top of everything else at a time which we can call the Big Bang. In an expanding universe, a Big Bang is sort of a natural occurrence, and indeed, astronomers went to great lengths to avoid Big Bangs before we sort of discovered the cosmic microwave background in 1964. So a Big Bang is sort of a natural occurrence. And we can think of this graphically if you just think of the galaxies moving apart since the time of the Big Bang. And if you look at the distance between galaxies and plot them, you can see at the time of the Big Bang, the galaxies are at the same spot, and they're moving apart, and more time goes on, the further apart they are. So that dotted line, this dotted line, is really how fast the universe is expanding, and it's related to the distance that the galaxies are apart divided by the velocity they're going apart. So it's kind of like a problem you would have done in 8th or 9th grade about trains leaving stations and when do they meet. So measuring how the universe is expanding, I should say, let me just go back to this diagram. If you go through and measure that slope of that dotted line, that's the trajectory of the universe, and it allows you, therefore, to extrapolate the universe back in time to the Big Bang. If you measure the slope of that dotted line, distance divided by velocity, you get the age of the universe. Now, I thought this was a pretty good thing to do in 1993 when I was doing my PhD, and this is my picture of my PhD thesis, showing it to my PhD supervisor, and you can see my Hubble diagram there. And I had measured the Hubble diagram in 1993 using supernovae, and it turns out some called type 2 supernovae we're not going to talk too much more about tonight, and was able to get an answer based on calculating how bright these things would appear based on how hot they were and how fast they were expanding. And so the value that I got was that the universe was about 14 billion years old. Now that was actually quite an unpopular answer in 1993 when I measured it. It turns out to be very close to what we think the correct answer is. We'll talk more about that. But it was kind of at the middle of a conversation we were having, and it was really decided with the Hubble Space Telescope especially, being able to make measurements of what are called Cepheid variable stars with great precision. And those are stars we can see in our own galaxy. And it turns out that the universe is expanding such that you might think its age is about 14 billion years old. Now, how do we actually put this into a framework that's not a cartoon? Well, that's Einstein's theory of general relativity. And it apocryphally, and this is almost certainly not true, but it's apocryphal, so everything with Einstein I think is apocryphal, is that in 1907 he saw someone fall off a building. And as he watched the person fall, presumably to their detriment, he didn't think, I'm going to go get an ambulance. He thought, I think that person feels weightlessness. I think the acceleration is exactly equal to the gravity, and I think that must always be true. And he spent the next 8 years trying to reconcile that idea that acceleration and just going faster are equivalent. So it's equivalent to saying you can't tell if you're in a rocket ship accelerating at 9.8 meters per second squared, or you're in a box sitting on Earth being accelerated by gravity of 9.8 meters per second squared. Those are equivalent. And Einstein's theory of general relativity rises out of making that statement true all the time. It's very complicated for those of you who get to learn it. You tend to have to make lots of simplifications to solve anything. But from it, it turns out black holes, gravitational waves, and as I'll show you, the understanding of cosmology all emerge from it. One of the things it predicted was that space would be curved. And that was something you could test very quickly. And so soon after he published his theory in 1915, people were able to go out and look at a solar eclipse where the sun would, of course, which is very massive, would be in front of stars. It would curve space, and when you curve space, you bend the light paths. So the light would then be distorted where the stars are in the sky. He could predict that with this theory. And then you come back, wait for the sun to be not eclipsed, move across the sky, look at that part of the sky, and see, did it happen? And the answer is, it did. It happened as he predicted. And this made Einstein famous, actually in a way that probably is not truly appreciated by most people. We always think of Einstein, famous, 1905, special relativity, E equals mc squared. If you're a physicist in the audience, photoelectric effect, etc. No. This is when he became a household name, because from pure thought alone, aesthetics, he came up with a theory that radically changed Newton's laws of gravity in terms of conception, not really in terms of most everyday life. And now 100 years later, 110 years later, we literally have never found a place where it's wrong. It gets the right answer every time. That is a story that does not happen in science very often. Copernicus sort of did it when he put the sun, for aesthetic reasons, in the center. It didn't actually predict things any better, but it was right eventually when we started seeing that the sun really was at the center. But almost all science is not someone coming up with an idea and then it's right. It's because they're trying to solve another problem. And Einstein turned out could solve a bunch of problems, the precession of Mercury, for example, but it really wasn't, he wasn't trying to fix precession of Mercury. That emerged as a solution or a thing that he could fix with this theory. So it's a truly special time in science that is worthy of celebration. But it is interesting that today, most people don't think of general relativity in the public as the thing that made Einstein famous, even though it was in 1920. So it turns out Newton really struggled trying to figure out how gravity would work in the entire universe. If the universe is without end, Newton was trying to say, how do I solve that problem? And he never really got to it. It turns out the solution to Newton's laws for a universe that is infinite, there's one solution. It's actually very simple. The universe has nothing in it. That's the solution. As soon as you put anything in it, there's no solution. Use Gauss's law if you're in the audience and studying physics. That's how you solve that problem. Very easy. All right. So when Einstein had this new theory, he could actually solve this problem. But when he did the solutions were dynamic. That meant the universe seemed to be in motion. And he looked around, said, it doesn't look like the universe is in motion to me. What should I do? And he wasn't sure, and then he suddenly, I've missed something in my equations. I can add something, which he called the cosmological constant. And we think of this constant as something that is energy that is part of space itself. It's not really the way he put it in, but you can think of it that way now. It's the easiest way to think about it. And the presence of this constant, it turns out in his equations, caused gravity to essentially push on itself. That is, this energy that was everywhere in space pushes on itself by gravity rather than pulling on itself like the atoms and stuff do. And so he thought maybe I could tweak this constant to offset what the gravity in the universe is, and I could make the universe steady. Great idea. It turns out it didn't work. It suffers from the butterfly effect, instability. If a butterfly flaps its wings here on Earth, the other side of the universe eventually becomes unstable. So it turned out not to be a good solution anyway. But he stuck with this for a long time. Later was quoted not as saying this was the dumbest thing I did in my life. He said, I acted like a donkey, sticking with it. And then when he got rid of it, he basically said, this is a distraction, it's relevant, I shouldn't worry about it, let's get rid of it. And it was banished, more or less, except for as things that could be in the equations, but were not necessary. But it did allow us to calculate very precisely what the universe and how it would be behaving. Turns out we had to make a big assumption, which for this audience I wouldn't normally tell, but this is a pretty smart audience, is that the universe is homogeneous. It's the same everywhere. And it turns out you can make sense of Einstein's equations with that assumption, which largely seems to be correct, like really seems to be correct, across the scale of the universe. And it allows you to make these solutions. And so essentially, if the universe has stuff in it, then the universe will slow down, and it slows down faster and faster over time the more stuff the universe has in it. The more density of material it has in it, the universe slows down faster and faster. It turns out if the universe is totally empty, totally devoid of anything, the universe doesn't slow down at all. It just keeps getting bigger and bigger, faster and faster. And if the universe has a lot of stuff in it, then the expansion will stop, halt, go in reverse, and you get a universe that they all begin with the Big Bang, but only the heavy universes end with the Ganab-Gib, the Big Bang in reverse. Okay. I told you that space can be curved. Well, Einstein covers that in the universe as well, because the universe can have a different geometry depending on its density. A heavy universe, it turns out, is closed. It's finite. It bends onto itself in a fourth dimension. In this universe, triangles add up to more than 180 degrees, just like they do here on Earth. We forget. In this room, triangles add up to 180 degrees because it's a tiny little patch of Earth. But if you try to connect Australia, India, and Antarctica, do this at home off a globe, you'll do your triangle and it adds up to more than 180 degrees. And that's because the Earth's curved. The universe can be curved just like that. Okay? If the universe is empty, it's light. It bends away from itself. Sort of has a springiness. And triangles add up to less than 180 degrees. And then there's this really interesting sweet spot where the universe is perfectly balanced between being heavy and light, the just right universe. This universe is flat. That is, triangles add up to 180 degrees. These are related also to the actual solutions I showed you of how the universe expands over time. If the universe is full of stuff and it's heavy, the universe has a beginning and an end. And that universe is finite as well. It has a beginning and an end, sort of. It's a finite universe, both in time and space. A universe that's light lasts forever. It also goes on forever. It's an infinite universe. And the just right universe, well, as I said, it has no curvature, and it kind of comes to rest an infinite time in the future. So it kind of just asymptotes to coming to halt an infinite time in the future. A beautiful symmetry of these equations. So one could imagine a way of actually doing an observational test. All you have to be able to do is look back in time, and it turns out you can do that because light only travels 300,000 kilometers per second. And if I look at objects that are billions of light years away, then I can look billions of light years in the past. So imagine I look at the things like supernovae that I studied, and I don't look just in the nearby universe. I look at really, really distant ones. I can measure distance and velocity back in time, and I can measure it to closer and closer objects, and I could see how the expansion rate of the universe changes over time. If it's not changing at all as I look back in time, well, that's a universe that's going to go on forever, right? It has not slowing down at all. On the other hand, there's this critical line of deceleration where if I'm on one side of that line, gravity wins, the universe is finite, and it ends. On the other side of that line, gravity loses, the universe expands forever, and it's light. One side of that line, the universe is closed, is curved onto itself. The other side, the universe is curved away from itself. And it turns out we had some new technology, both on astronomy side and on the high-tech side, actually fed a lot by astronomy, that happened as I finished my PhD in 1993. The first thing is a supernova of a different type than I studied, a type 1a supernova. And these are amazing explosions that take about 20 days to shine 5 billion times brighter than our sun. They produce more than half the iron in the universe. So the things you're sitting on here today have stuff probably imported from Australia and from these exploding stars. That's what you're sitting on. All right? These are interesting objects because they were theoretically thought about by the name of this, the Chandrasekhar, who this theater is named after. He didn't exactly win his Nobel Prize for this, but it was a big reason because it was a whole body of work he won it for. And this is probably his most famous piece of work, where he realized that a star, a remnant of the center of a star like our sun, if it got to a very specific mass of 1.383 times the mass of the sun, its gravitational, essentially its gravitation would overwhelm the ability of electrons to push against that, and the thing would start to collapse. And what we know now is they start to collapse. They actually create a thermonuclear bomb that's, 1 million times bigger than the Earth, rather than just a little one. They explode, make all this iron, but they're also really useful ways of measuring distances. A group in Chile used these things and went out and observed them for several years and realized they could be calibrated to measure distances to about 7%. Now, 7% doesn't sound wonderful probably to this audience, but back in 1993, 1994, everything else was 30 or 40%. And these things are so bright, I could see them with the other technological advancement, digital cameras. So your digital cameras, we've been using digital cameras in astronomy for, since the late 1980s, way before there were consumers products. And they're much, much more sensitive than film we had before. And we could go through and detect these very rare objects with the first large digital cameras that were put on telescopes in 1994. So here is what one of those images looks like. We would take 1,500 of these images in a night. This is an 8 megapixel camera, or 8 megapixel image. There were actually 8 of them taken at a time, so kind of a 64 million pixel camera, which is still pretty respectable. This is 1994. And in all of these images we would take, there would be like several thousand galaxies in each of these images. There would be 3 exploding stars in all of that data we took a night, about 50 gigabytes. Now 50 gigabytes, but the biggest hard drive we had in 1994 was a gigabyte. okay? So I had to get 50 of these hard drives just to take the data. And you know, my iPhone is so much faster, so much more storage than we have now. So it was actually quite a big task to go through and write the software that would discover these needles in the haystack. So a needle in a haystack looks like this. That little block up there has a star in it that exploded, and the reason we know that is because we take two images. We take a before and an after, and then we have to discover these things. So this object, it turns out, was about 5 billion light years in distance, e.g. it was exploded before the Earth was formed. Right? So you can really go back as in this time machine. Now, the actual discovering of these things was chaos. And I bring you to Chile back at this time to a movie that we managed to have made while we were doing this. So we only get 6 nights on this telescope a year. It's one of the most prized telescopes in the world. That's one of the biggest allocations of any group in the world. Every photon is important. The data comes in. We're at the telescope making sure everything's fine. I'm trying to get my software fired up to go through and try to subtract data and look through it. But the reality is it finds a lot of garbage. I have a little 2-layer neural network, an early version of AI going, it was okay, but it's not very good compared to humans. So literally a sweatshop of astronomers going through, going, yep, nope, nope, maybe, yep, nope, nope. And time is of the essence because we have to get a spectrum of this. And we need the largest telescope on the planet, the Keck telescope, which is in Hawaii. And we have time scheduled in advance, 36 hours after this night. So we got to get all this stuff done and to them. And there you can see the Keck telescope, Adam Rees, who I won the Nobel Prize with, Alex Filippenko on the team, getting ready to observe the objects that we sent them from the process. I didn't sleep well. I got heart palpitations from not, staying up 24 hours in a row, several days, trying to make things work. But at the end of about 4 years of work, we had 15 objects to look at. And when we looked at them, this is what the real data looks like. This is, remember, it's the same diagram I showed you as our thought experiment of looking in the past. And here we have every supernova makes a measurement of d divided by v. And there's uncertainty, so those are error bars. So it turns out those error bars are 68% of the time the answer lies in there. And what you can see, just straight out of your eye, that if you compare the nearby objects and the distant ones, those distant objects, not a single one is in the bottom part of the diagram, even with the uncertainty. The universe is not going to end in a Gnab-Gib. And I was kind of sad because that was kind of what I was cheering for. I like the idea of it. The universe begins, it ends. How good would that be? But when we looked more carefully, we realized, well, a couple of the error bars extend in the yellow part where gravity is slowing the universe down. On average, they really lie above the line. That is that the universe was expanding slower in the past and had sped up. And it's for that that we received the Nobel Prize in 2011. It was a huge surprise that somehow, thank the team. If you ever see any of my team members, give them a big hug, right? Because it was a big team effort. So you don't get that type of surprise often in life. When you see it for the first time, you don't go eureka. You go, oh God, what have I done wrong for the last 3.5 years of my life, all right? So it took us a lot of time figuring things out. And of course, you have to go out and tell everyone. And the entire world gets to grade your homework, right? And not just for a week, for the rest of your life. People are still grading my homework. If you're one of the people who's written me in the last week to tell me how I got it wrong, thank you very much. I appreciate it. But I literally get emails every week to this day. So what our measurement indicated was that Einstein's cosmological constant, which we generically refer to dark energy, because maybe it's not Einstein's version of things, well, that is the thing that makes gravity push rather than pull. Okay? So his big mistake is really the thing that we seem to have uncovered. But just to give you a sense of what this means, it really does change the past, the trajectory. So this is what general relativity told you without a cosmological constant the future of the universe looks like. This is what our measurements said, the red line. Now, the cosmological constant is part of space itself. It has a density that never changes. It's in you, it's in me, it's in every part of the universe. It's at the time of the Big Bang or right after the Big Bang. It will be that way forever into the future. That's what Einstein's Big Bang cosmological constant says. So the way it works is the universe was born with the cosmological constant it has now, but the universe was really hot and dense. It was irrelevant. It's only as the universe has expanded that dark energy has been able to take over. And that happened 6.5 billion years ago. So in this diagram, the universe is slowing down because it's heavy. Dark energy takes over here. And now, sorry, I've got something in my throat. And now it's an exponential process where it just pushes the universe apart faster and faster over time. That's what our measurement seems to say. It's kind of crazy. I don't like it. But I've learned the universe doesn't care what I think. It just does what it does. And my job as a scientist is to actually measure it and not be too judgmental. So the detailed analysis was that the universe needed to be 70% this dark energy and 30% normal gravity that pulls. It had to be a mix of sort of 70-30. Now you can imagine people were skeptical, as they should be. I was skeptical. I mean, I knew I had done everything I could to figure out what this stuff was, but there are those pesky unknown unknowns, the things no one has thought about that we had to worry about, okay? So the best thing to do is to do an experiment in a completely different way. And it turns out that nature gave us what turns out to be like a Rosetta Stone, the cosmic microwave background. Now, those bumps and wiggles you see up there are actually sound waves. And yes, the universe can have sound waves. They just have to be very long wave sound waves. So you're not going to hear yourself scream, but there's still sound out in the universe, just light years long. And so because sound waves are things we can understand and do extremely well here on Earth, and the fact is that the Big Bang kind of shook the universe up in a particular way, and then we can see how the sound waves should end up from that process. And it turns out that what the universe is made out of affects what the sound waves look like. If the universe is made out of honey and you throw a rock in it, you get a different splash pattern than if it's made out of water. And so the Big Bang is like throwing a bunch of different sized rocks, and you can go through and calculate what the sound waves look like, and then you can look at the cosmic microwave background and say, what does the splash marks look like in reality? And it turns out there's so much information here that you can do this exquisitely accurately. So I'll show you the data. This is the actual data from the Planck experiment. And what we're measuring here is how many sound waves there are of different sizes. And you can see that the prediction by the black curve is there should be a bunch of sound waves about 1 degree across. And there is, because the little red dots are the actual data from the sky. Now, if you're a physicist, you know immediately you don't by accident get data and your theory to look this coincident. That just doesn't happen. It's not an accident. It would never happen anywhere in the universe at any time since the Big Bang by accident. It's not a random. We really do seem to be able to predict what we are seeing in the universe. And that curve is more or less what we would have predicted in 1998. So if people ask me, do you think the universe is accelerating? And the answer I would say is yes. But I think as much because of this than what I did. This is something that's not going to go away. And what it tells us, interestingly, is that 25% of the universe needs to be stuff that I haven't talked to you yet about, but I'm sure you've heard of, dark matter. It's stuff that has gravity, just like atoms, but it can go right through itself, go right through the Earth. It doesn't seem to interact with anything except for by gravity. And if you don't have 25% of the universe being this dark matter, you cannot make that curve work. It is essentially, I would say, no one has shown a credible way to me that you can get rid of dark matter. And I'm sure we'll have questions about this later on. I'm going to point him to that picture. Okay? So dark matter, we don't know what it is. We suspect it might be a particle, as I said, like the neutrino that can go right through the Earth, but it's not really predicted in the standard model, and as I'll show you, we've never really been able, we tried hard to look for it, and we haven't found it. The other thing we can do in this experiment is look at how big the sound waves are. So we can use physics to calculate how long the sound waves are in meters, and then we can see how big they appear. And the curvature of the universe magnifies or demagnifies those sound waves. Okay? So just like the front and back of a spoon, you have a different size depending on the curvature. So you can go through and calculate how big those bumps are compared to what they see, and that tells you the geometry of the universe. Now, it's exactly flat. I mean, we're talking, because you've got such good measurements, to 1 part in 1,000. It is flat. One thing I haven't told you is that when you're calculating what contributes to make the universe flat, you get to throw everything in. You get to throw the cosmological constant in, you get to throw neutrinos, photons, anything that has energy or mass contributes. Okay? So everything, if we do some cosmic subtraction, everything adds up to 100% of the amount of matter to make the universe just right. We know that roughly 25% of it's dark matter from the cosmic microwave background, 5% of it is atomic matter, and that leaves the 70% mystery matter that we discovered left. Any way you look at the universe, it seems to be this mess, where 5% of the universe are the atoms that we can measure. Every Nobel Prize, other than mine, is that 5%. "95% of the universe we have to make up. We've never seen it. The only way we know it exists is through astronomy." And if you're shrewd and like a little cynical, you might say, "Professor Schmidt, if you need to make up 95% of the universe, doesn't it mean you just don't know what you're doing?" That's fair. But let me remind you that curve I showed you from the cosmic microwave background. That was predicted with theory before we made the measurement, based on this idea. Science is about having an idea, making predictions, and as long as you get the predictions right all the time, you kind of say that's the way the world is. Now, sometimes we're wrong. Newton's theory predicted things for 300 years without fail, and it turned out not to be perfect, exactly right. So I can't guarantee what I'm showing you here is exactly right, but to first order, it seems to be the way the universe is. I don't like it, but as I said, the universe doesn't care. So we really don't know what dark matter and dark energy are. And one of the things we've been looking at are different ways to look for it. So you might think you could create it in CERN, the Large Hadron Collider. Now, the way you detect it is things would bump into each other. You'd make a dark matter particle, but that requires dark matter particles to actually interact a little bit with something. The dark matter particle you can't detect. It just leaves the building. And then you add up with everything's left, and you're like, whoa, I'm missing some mass. Something has left. So that was the hope. Well, nothing yet. No sign of it. Not even a smidgen. You might hope that occasionally it will run into an atom and disrupt that atom. So people have put together elaborate experiments where we take tons upon tons of xenon liquefied. Why? It's a liquid, inert, really heavy gas. Stick it in a mine underneath the Earth so nothing else can hit it, and wait for years for a dark matter particle to hit an atom of xenon and go ping. Okay? Literally ping. It's a phonon. At this point, nothing. Nothing has been seen. And we're beginning, it turns out, to run out. If we make the experiments much bigger, it turns out neutrinos are going to start pinging the xenon, and we're not going to be able to see anything. The final way you might hope to see it is that it does interact, and in the extreme versions of astronomy or astrophysical situations, you might see it interact with itself or with matter. We've had some exciting moments, but stupid things like pulsars seem to have gotten in the way. So at this point, it's not clear that there's any evidence in any avenue for what dark matter might be. We continue to look, but I'm here to tell you, we've tried hard and we haven't figured it out yet. So I don't know what's going to happen there. Maybe someone will figure it out, or maybe it will continue to be a mystery. So what is dark energy? Well, the only way we know how to measure dark energy is through gravity, is measuring the expansion rate of the universe really, really accurately and saying, is it exactly what Einstein said, or is it a little different? Okay? So people have been going and doing huge experiments, including expanding the supernova measurements. So now there are literally thousands upon thousands of them. And what you can see, the black line is what we got in 1998. And I would say I passed my exam on this one. We're getting exactly the same answer we did in 1998, even with 100 times more data. And so this data is been largely consistent, and I'll talk just a little bit in a second. It turns out the next line of data, which I have a figure, it just doesn't work so well in a public talk, shows a tiny, tiny issue where maybe right here, where there's not very much data, there's a deviation. Maybe. I'm not convinced yet, I'll be honest. But we have other ways of measuring distances, which are these sound waves. Because remember I told you these sound waves become galaxies. And we can see the bumps and wiggles in the galaxies of today, because the galaxies, when we go do a map of the sky with millions upon millions of galaxies, we see the ripples of the Big Bang in these galaxies. So you can actually see those bumps that I told you about in these galaxy patterns if you analyze it very carefully. And here is the most recent measurements made from an experiment using one of the 4-meter telescopes in the United States. And effectively, you can go through and compare the bump relative to the cosmic microwave background right after the Big Bang. The black line on one is Einstein's theory, and right here, it looks, again, unfortunately, where the data is the worst, that maybe there's a deviation. Now, if you do a formal measurement and you say, is Einstein right or wrong? I would say right now it's not convincing that Einstein is wrong. But if you think you know how the universe might be different than Einstein, then sort of at a 99 and a bit percent level, you can say, oh, it looks a little different. Right now, I would say we need to get more data. But if this is real, if the universe really isn't doing what Einstein predicted, that would be huge. Because it would be the first glimpse we have about trying to understand what this dark energy is. Because if it is what Einstein said, it's kind of, that's the way the universe was born, just suck it up, kid, and go on, okay? But if it's changing, then it's something different. We'll see. The beautiful thing is we don't know. Science evolves. The story keeps going on. All right. There is another problem. My colleague Adam Rees has been focused for the last 20 years at measuring the Hubble constant really accurately. The cosmic microwave background, it turns out, measures how fast the universe was expanding, the Hubble constant, back right after the Big Bang. And because it's measured so accurately, we can bring it to the present day and compare it to the work that Adam and others are doing in the nearby universe. And the numbers have been getting further and further apart over time, such that right now you're kind of 99.95% sure there's a problem. Adam is my academic younger brother. That is, I did my PhD, he was 3 years behind me in the same group. So I can tell you there was nothing I would like better than to show him wrong. But I'm going to be honest, I haven't been able to find any mistakes. Okay? I have worked a few times. I'm continuing to work on this problem in a different angle just to check it out, but I think there's a genuine issue here. I have not heard a single credible way to fix this problem. Not a single credible way. Now, maybe there is a credible way and I'm just too dumb to realize it, but I think this is becoming a serious issue. And when you get a little crack in the big stories, sometimes revolutions occur. So this is also something I think that is very exciting, but I have no idea how to fix it. And then I'll remind you there's all these other things that are happening. The James Webb Space Telescope is finding galaxies that are way bigger and brighter than we would have expected right after the Big Bang. We have the Square Kilometre Array coming on, looking at these galaxies in the future. We have LIGO, and hopefully LIGO India, being worked on by people in this audience, able to go through and find merging black holes. And there are way more black holes that are bigger than we would have ever guessed. This is all really exciting stuff. Indeed, there are evidence that there are black holes that are way too big right after the Big Bang. So there's some physics of black holes that needs to be understood. And of course, we can go and in the center of the nearest by galaxies like M87, that we've always known has had this jet coming out of it, we can go through and look at it now with radio telescopes and literally see the shadowing effect of the black hole on the light of stuff around the black hole. And so that hole there is really where the black hole is. And we're getting better and better measurements of this. And it demonstrates that black holes really exist, and they're millions to billions of times bigger than our sun. So there's still a whole bunch of things to do in cosmology. And then we have other things, like going out and looking for the signs of life with the next generation of giant telescopes. We had what I think will be ultimately seen as a false start on this in the last couple months. But let's see. But we're going to have the opportunity to look in and look for signs of things that really can only be explained in planet atmospheres with the next generation of telescopes by things like life. Now, of course, if life doesn't exist in any frequency outside, we won't see that. But it would not surprise me if bacterial life isn't quite common in planets. We'll see. The beautiful thing is we can test it. So there's so many things to do that are so exciting. Of course, we have, the question that, the age-old question that's always asked to me is, maybe not in this audience, but my minister always asks me this. Brian, this is really cool stuff, but why do I pay you to do this? And the answer I always tell them is it's useful. Look at your iPhone. So my area of astroparticle physics, which is about as abstract and far from Earth as you can imagine, has helped bring in the CMOS camera. That's from the trip to Jupiter. It was invented for that. The World Wide Web and the touchscreen both come from CERN. You've got GPS creating high precision time measuring devices, being able to launch them in space and use general relativity. And of course, radio astronomy, people in this audience will know, help contribute to Wi-Fi. And if you just look at the history of the iPhone and all the discoveries that contributed to it, these are discoveries which were not applied discoveries. These were discoveries made as part people just going and trying to understand the universe. And it goes back into time. And so progress isn't something you design. It's something that emerges. And yes, you need people to translate crazy things that I and others like me come up with. But you also need to come up with the ideas so that there's this sea of ideas of which to innovate from. So one of the things I'm doing now is I am out working with startup companies using technology from discovering gravitational waves. And we can do a whole bunch of cool things with that technology. And you can really see when you get into that how the whole process works. You don't just invent things because you know they're going to be useful. You don't know they're going to be useful until you do the type of work we're doing here. In our future, well, the sun, I'm sorry to say, is nuclear reactors getting hotter and more energetic over time. And so over the next billion years, our oceans are going to boil off, and there's not much we're going to do about that, except for maybe create a giant sunscreen around the Earth, but I think that's probably a bit of a stretch. A billion years is a long time. 6 billion years from now, give or take a billion, the sun is going to switch how it burns its hydrogen and helium, and it's going to puff up and almost certainly destroy the Earth completely. Not just boil our oceans, but vaporize us. Then it'll die, and then there'll be nothing to be around anyway. So the Earth has, depending on how you want to think of it, 1 billion, or maybe if we can move out to Enceladus or something, 5 or 6 billion years to go. But the future of the universe is actually quite interesting. It's dark energy, because dark energy is expanding the universe, and it is able to exponentially expand the universe, as I showed you. The more space expands, the more dark energy is there to push on it. So you get exponential expansion such that the essentially things we see now, galaxies we see now, the light that's emitted is going to try to get to us. It's going to travel through space. Space is going to be created so fast that the photon can't actually move through the created space fast enough to get to us. So things we see right now, they're not going to be there in the future. The universe is literally, unless dark energy suddenly disappears, going to fade away over time. So the universe will at an ever-increasing rate expand, fade away, and that means there's never been a better time to be a cosmologist, because the future cosmologists will have nothing to see. Thank you. We're going to do questions? All right.
Thank you so much for the lecture. We have a full house here, as you can see, and I'm sure there will be a lot of questions. So the audience can raise their hands, and if you want to ask some relevant questions relevant to the talk, then we'll come to you with a microphone, and you can use that to ask a few questions.
And don't think you need to try to ask such a hard question that I'm not going to be able to answer it.
Perfect chance for you.
Yeah, well, okay.
We'll come to you
He's in charge.
With some microphones. We can start with question there.
Wait just a second.
Please switch on the microphones when you give them.
Hello.
Thank you.
My question is, can we say that dark matter is something like the quantized version of gravitons or gravity, or is it analogous to gravitons?
So we think gravitons, if they exist, are going to be at a very different energy level. Okay, so I think it's very unlikely that that would work. There are all sorts, like innumerable ideas for what dark matter might be in terms of particles. There are ideas of super light particles that end up actually having quantum wavelengths the size of galaxies, so they're fuzzy. We have things that we can't measure at all. We have, what happens if dark matter doesn't interact with anything other than gravity? Then we're kind of stuck, right? So there are lots of ideas. We try to test them, but at this point, as I said, we haven't been able to find anything. So the challenge is finding an idea that's right that we can test. Because we can come up with lots of ideas that are untestable. Those aren't very interesting. Because science is about having an idea and testing it. And if you have an idea, even if it's right, some omniscient being knows it's right, but there's no way to test it, it's not very useful from a science point of view.
Thank you. It was really interesting. So the graph you showed, the separation versus time, it didn't start from the origin. It started like it started a few parts in positive x-axis. So why?
Because I don't know where the origin is. So it's arbitrary time. What I know is we're right now at 0. So in that diagram, where we are right now is 0. And I go to the left until I cross the line. That's the time of the Big Bang. So I don't know when t equals 0 is. By definition, it's when the line crosses the y-axis. So that's where you would then say this is time equals 0. That's the time of the Big Bang. So it's literally it's relative time if you want to think about it, because I don't actually know when the Big Bang is. I just know it's back in time somewhere. So it works. Yeah. Thanks.
Let's try to make the questions homogeneously distributed. Could we have some on this side as well?
Sorry.
Yeah, a really interesting talk. What do you think of the many worlds theory, and do you think everyday decisions are quantum events that create parallel universes?
What was the first part of the question?
What do you think of the many worlds theory or many worlds interpretation of the
what do you think of the multiverse theory?
Oh, the multiverse theory. Okay. So, multiverse theory. The problem with the multiverse theory is there's a lot where it kind of feels right, but we haven't figured out how to test it. So we need to keep thinking of ways where the multiverse, and the multiverse, just to be clear, what I would say, and this is a problem of a definition, what is the universe? My definition of the universe is anything and everything we could ever know. A multiverse would be something beyond that. That would be presumably different in some way than our universe. And so almost by definition it becomes difficult to test the multiverse theory, because if I could test it, then it's kind of part of my universe because I can interact with it in some way. So it turns out from a sort of a philosophical point of view, there's many things that would make a lot more sense if there was an infinite number of universes. You have the question is, how do you have a universe with a beginning? Does that make sense? Would it make sense that the universe of all universes has always been and always will be in some world? You get into complexities about what do we mean by time and stuff I don't want to go into. It's not my area of specialty. And then the other question about the idea of parallel universes. So my office mate is a guy by the name of, my PhD office mate was Sean Carroll, who's written on this stuff. And Sean really does believe in this multi-world hypothesis where you go off and every universe is replicated. Okay, fine. I see no evidence for it. Sean is a lot smarter than me, but it still doesn't make sense to me. So I make fun of Sean whenever I'm with him while we're drinking wine. And then he just tells me I'm an idiot.
Hello. Good evening, sir.
Sorry, wave your hand. I got to figure out where you're at. Oh, there we go.
Sir, so for the past few decades, physicists have been trying to reconcile quantum field theory with Einstein's theory, right? And so one of the things that they have been thinking about is that the vacuum energy of the universe is kind of thought to be as an equivalent to the cosmological constant. And when we do that, it leads to the what is known as the worst theoretical prediction in the history of physics, where the vacuum energy is 120 magnitudes different than the cosmological constant. So what do you think moving forward in future is going to be this reconciliation of quantum theory with general theory of relativity?
So, yeah, there's this issue, which is that if you just kind of naively use the idea that you can essentially get spontaneous creation of particles, and they come together and quickly, Heisenberg's uncertainty theory, then you expect to have, so much of what looks like energy in space that the universe would have exponentially expanded when it was a fraction of a second old, and we would have never been here. So Steven Weinberg, who recently passed away, but one of the great physicists of all times, thought about this back in 1984. And he was thinking, I don't know how to get rid of this. Well, actually, you could imagine if there's an infinite number of universes, you expect most of them to have that vacuum energy we've just talked about, but there will be this probability distribution of them not. And so then his prediction was that would mean that in the infinite number of universes, we would only exist in a universe that lived long enough for us to exist. Cosmological constant would stop galaxies from existing. And he went through and calculated and said, well, that means the cosmological constant has to be the essentially the smallest number where we could exist. And he said it's about 0.8 is the value. The number we measure is 0.7. So he did that in 1984. The problem is we call this an anthropic principle, where we only can live in universes that we can exist in. Fair enough. But it doesn't really predict anything. How do you test it? It assumes there's an infinite number of universes. There's a lot of assumptions there. So I can't tell you it's wrong, but it doesn't really provide a satisfactory solution. But maybe that's what's going on, and someone will come up with a clever way to get some more detail on it.
Question from that side, please.
Hello, sir. So I have two questions. So these questions might be less silly. So the first question is that you show the graph, a pie chart of the 5% of the atoms, 25% of the dark matter, and 70% of the dark energy. If we don't know the 95%, how do we come up with this percentage? And the second question is, if the universe is expanding, so the dark energy is getting more contribution, so that 70% can go up, or
Yep.
will...
Okay, understand the question. So the first question is, we know the percentages, most easily explained, I think, by the cosmic microwave background. It literally tells you everything adds up to 100%, and I can tell you 25% is dark matter and 5% are atoms. And then the 70%, it gives you an inkling of as well, although it really helps to have the supernovae. It says, actually, I need to have the universe speed up a little bit to get those things to be exactly the right size. So it turns out you kind of get all the numbers at the same time from the cosmic microwave background, but it needs a little help from the supernovae. But you're right, as the universe, imagine the universe is 14 billion years old right now. Imagine I come back in 28 billion years, okay? So another 14 billion years when the universe is 28 billion years old. The universe turns out to have expanded by more than a factor of 2 during that time. It will be 8 times, therefore, more volume, and it means that the density of dark matter and atoms will have dropped by an 8. So instead of being like 0.3, it's going to be almost like 0.05 at the time. So those numbers do change in proportion over time. If you come back 100 billion years from now, the fraction of the universe that's dark energy will be almost 100%. And it runs away with the universe. How it runs away with the universe is by essentially getting bigger and bigger, faster and faster, and leaving everything else more or less behind.
What would particle physics look like if space-time had more than one time dimension?
Did you get that?
What would
physics
particle
be like if the space-time had more dimensions?
What would particle physics be like if space-time had more dimensions? It really depends on the nature of those dimensions. So string theory is all about having 10, 11, or maybe even 12, and figuring out if we can actually make the universe as we know it work with those extra degrees of freedom. And it sort of works, but string theory really does not like the cosmological constant. They have to go through all sorts of crazy things, basically saying we're kind of a almost infinitely improbable universe to make it work, but that's what Steven Weinberg had to do to get rid of the cosmological constant. So the same basic idea. So it turns out when you have lots of dimensions, you have what we would describe in physics as lots of degrees of freedom. So I can honestly say anything is pretty much possible in a universe where you're allowed that much freedom as a theorist. But it is one way to try to reconcile how to bring gravity in with the other forces of nature. And some of those dimensions can be really small, wrapped up all around us in weird ways, and make gravity, for example, not go as 1 over r squared when you get down to, let's say, nanometer scales. And we're trying to measure that. It's really hard. Thus far, gravity seems to be okay, down to almost a micron. But we keep looking, so these are all things we can test.
The younger ones want to ask any questions? We can give one question here. Yes, that. Maybe behind you. Yeah. Younger ones also can raise your hands if.
Good evening, sir. So my question is, universe is expanding, all right. And if we see the balloon analogy of that, the balloon is stretching and the dots are moving apart from each other. But that balloon is also occupying some volume in the space. And like that, universe is expanding into what?
So, in the balloon one, it's quite a nice thing. So imagine the balloon. Oh, thank you. Imagine the balloon is a tiny point at the time of the Big Bang. And we're thinking in multi-dimensions here, so you got to have time as well. So the balloon is going out in time and getting bigger and bigger. What's it expanding? It's kind of expanding into time, if you think about it. Okay? So you've got this extra dimension. So I always like to say the universe is expanding into the future. But the problem is you're trying to envision that 4th dimension. And trying to visualize 4 dimensions in your brain is really hard. Okay? And I always say, I have met a few people who think they can visualize 4 dimensions. You do not want to be one of those people. Okay? So mathematically, this is where math is good. Okay? You can start doing triangles, and it turns out that a triangle with time as a dimension, you kind of go, x squared plus y squared plus z squared minus ct squared. That's what a triangle looks like in 4 dimensions. So you have a mathematical way to figure it out. It's just really hard to think of it up here. Okay?
Question from a tiny dot there.
I'm Aditya Nikhil Mahajan. I'm 8 years old.
Hello.
What is your question? Yes.
I honestly don't know what.
Okay. You can ask any question. I'll ask you a question. Is Pluto a planet?
Depends on which person you ask.
Ah.
Okay. So let's get on. We have only time for three more questions. So yeah, we can.
Hello, sir. The,
Right up close.
yeah. Am I audible?
I can hear you now.
Okay, perfect. So there was one theory I had heard that fundamental particles of the universe, maybe one of those, I the specific one, I don't really recall, but there's a fundamental particle which is metastable or unstable. So we have, say, 5% atoms, some other percentage of dark energy, and much more of other things. So in this particular case, down the line, if that fundamental particle is unstable and it breaks down, so it's something like we have the local minima and we have more fuel put in, we just have a spark of that particle breaking down. So that theory of maybe the universe ripping itself apart or maybe burning itself, does that kind of
It is, so there's all sorts of particle theories that sort of have versions of this. And so I haven't talked about today, but there's this sense that the universe probably went through exponential expansion and stopped right after the Big Bang, or this is what the Big Bang is, unclear. We call that inflation. And we think it is related to a particle, which we normally call the inflaton, that essentially gives rise to dark energy. It then decays, and that decay process kind of shapes the universe into the way it is today. So it could be that's what's going on now, and that's why it's kind of exciting. If dark energy is changing, some sort of process like that might be at work. And then if that's really happening, I have no idea what's going to happen to the universe in the future right now, because it all depends on what that particle does. Okay? So while I have sounded incredibly confident about everything tonight, if the universe is full of something I didn't know about that magically appears, like that could happen, it can change the story. I don't think we will ever know in my lifetime that it happens, but who knows, maybe we can get a sense of this dark energy changing, and maybe that's what's going on. I just don't know at this point, but it is possible. Yeah.
Go for one last question from the young one.
So, sir, what do you think about the Albert Einstein had predicted in 1916 about the gravitational waves? So, what do you think about that, sir?
What do I think about gravitational waves? Well, I